Alrighty. If you have received this particular assignment, then you failed the fourth marking period, the fourth 6 weeks. Now I'm going to send you a series of slide decks and then send you a retake. You'll be able to use any notes that you have on your retake. So I would strongly advise you to pause this video now and make sure that you have paper and pencil and that you take really good notes. All right, let's get started. Now, the first thing to look at is what is a radical? Well, a radical is anything under a radical symbol, such as a square root or a cube root. Now, a radical function has a radical expression with the independent variable, such as the square root of x plus 3, the cube root of x minus 1, the fifth root of x minus 1. Now, in this unit, we really zeroed in on square root and cube root, but you need to be aware that a root, in other words, this little number up here, could be any number. So let's take a look at the square root function. It is y is equal to the square root of x. That's the parent function, the most simple form of a square root function. Now here's what the graph looks like. Here's what the table looks like. I want you to take particular note of the points 0, 0 and the points 1, 1. Those will be important when we get to the topic of transformations. The domain of the square root parent function is 0 to positive infinity, and the range is the same. The x and y intercepts are both 0, 0, so that makes it easy for us. And the key points, as I mentioned before, that we really want to pay attention to are 0, 0 and 1, 1. Now, there are some restrictions with the square root parent function or any square root function. Whatever's under the square root cannot be negative. That does not mean that there can't be negative numbers there. But once you get done analyzing the expression, it can't be negative. Why? Because you can't take the square root of a negative number and get a real number answer. So, for example, the square root of 14 is okay, but the square root of negative 4 is not. It is undefined. And you can see that on our graph. If you go to x equal negative 4, there are no y values. That's because the function does not exist there. Now, another example. What if we had the square root of x plus 2? Well, it would be fine to have x be equal to negative 2 because then x plus 2 is equal to 0, and the square root of 0 is 0, so that's fine. But if x is negative 3, negative 3 plus 2 is negative 1, and we cannot take the square root of negative 1 and get a real number answer. So that is undefined. Pay attention to any restrictions that you might have in your square root parent function. That will be important for your domain and range. All right, so let's transition to transformations. This is the transformation form of the square root parent function. We have A, B, C, and D. You are familiar with all of those, but we're going to do a pretty good review just in case. So let's start with A, vertical stretch, vertical compression, and if A is less than 0, that should read vertical reflection. So change this compression to reflection. Now let's take a good look at what that might look like on Desmos. So I'm going to Desmos. I am already logged in on Desmos, and we're going to just take a look at the parent function. I have it graphed here, and I have the key reference point 0, 0, and 1, 0 all mapped out for you. Now, how does this graph change if we do a vertical stretch of 2? Well, let's take a look. Here we go. Now, the one thing I want you to notice is that when we do this vertical stretch, the point 1, 1 becomes the point 1, 2. That's because we took the output y, which was 1, and we multiplied it by 2. So if you are comparing the purple graph to the red graph, even if the red graph wasn't there, you know that 1, 1 is a key reference point for the parent function for the square root of x. You see that you have a graph that has 1, 2. You know that a vertical stretch of 2 has been applied. All right, enough of vertical stretches. What happens if we do a vertical compression? So we're going to compress this thing by 1/2. You can see the function over here on the left. And again, we see that the y value of our reference point was decreased by 1/2. We multiplied 1 by 1/2, and there we are. We have our label there. Okay, so enough of vertical stretches and compressions. Vertical transformations always affect the y value. So what happens if we do a vertical reflection? So I have done one here. It is also red, but you can see that the graph, the parent function graph, has been reflected perfectly, vertically reflected. And because vertical transformations always affect the y value, we can see that our new y value for our reference point is -1. And last, what happens if we do a vertical stretch and a compression? Well, let's see. Here I did a vertical reflection and a stretch by a factor of 3. Now, as you can see, our reference point 1, 1 is now multiplied by 3 and reflected. So it becomes 1, -3. Now, this particular Desmos chart is in your slide package. I will also be sharing a copy with you so that you can manipulate it and play with it as you see fit. All righty. Enough of that. Let's go back to our slide deck. So hopefully you get a clue on vertical stretches and compressions and how to analyze those. Now, shifts up and down are really easy. I'm not going to go to Desmos. I just printed a graph here. The red one, that's the parent function. If we shift up 2, then the 0, 0 point goes up 2. And if we go down 2, the 0, 0 point goes down 2. So hopefully you'll be able to analyze that pretty quickly. Let's take a look at the parameter B. Now the parameter B is horizontal compression, stretches, and reflections. And it is a little bit different from A. So make sure you take your time here and really understand. If B is greater than 1, it is a horizontal compression. If B is less than 1 but greater than 0, it's a horizontal stretch. And in both cases, it's by a factor of 1 over B. If B is negative, then we have a horizontal reflection. So for example, if I had y is equal to the square root of 3x, then I have a horizontal compression by a factor of 1/3. If I had the square root of 1/2 x all under the square root, then I have a horizontal stretch by a factor of 2/1, or 2. And if what's inside, if I have the square root of -x, then I have a horizontal reflection. Now let's take a look at that on Desmos and see what we can see. All right, so this is the parent function here in black, and you see our key reference points, 0, 0, and 1, 1, labeled here. Now, if I do a horizontal compression by a factor of 1/4, then I see that my reference point of 0, 0 is exactly the same, but my reference point of 1, 1 is now 1, 2. If I do a horizontal stretch by 1/4, then I end up with a reference point of 1 and 1/2. The most interesting one here, though, is definitely the horizontal reflection. So here on the left, you'll see I have y is equal to the square root of -4x. So let's see what that looks like. Wow, that is a horizontal reflection. So you can see it has been reflected across the y-axis. That's because this is horizontal. So everything that's happening is going to be horizontal, not vertical. All righty. And this was also compressed by 4. So I have a new reference point here. Whoops, let me go back here. Of -1 and 2. And if I also did a horizontal stretch by a factor of 4, then I would have a new reference point of -1 and 1/4. All right, now it's not all that important for you to understand how these look. It is very important that you understand the effect and can describe it using words when you see those kinds of transformations done to a function. All right, back to our slides. Don't forget, pause frequently and take good notes because you'll be able to use those notes on your retake. Okay, now moving left and right, that's pretty easy. It's transformations like you know and love it. If it's plus the C value, then it's moving to the left, C units. And if it's minus the C value, it's moving to the right, C units. So that's just like all the other functions we have studied this year. But there is one more thing about the parameter B that I want you to know. You notice that in the transformation form, B is factored out. See, it's B and then parentheses, and then the x minus C is in the parentheses. That means B has been factored out. The reason why is really, really important, so make sure you understand this and take great notes. Check this out. I have here a graph of a square root function that has been horizontally compressed by a factor of 1/3 and shifted to the right 2. But If you were to go to Desmos and type in y is equal to the square root of 3x minus 6, you would see that that has also been horizontally compressed by a factor of 1/3 and shifted to the right too. It's the exact same graph that we see here. Now, why is that? Because if you factor 3 out of 3x minus 6, you get 3 times x minus 2, which we already determined was horizontally compressed by 1/3 and shifted to the right 2. So the moral of this story is this: always, always, always factor b out if you need to. Now, sometimes you won't need to, but if you have a b value and there are no parentheses, such as 3x minus 6, I have a b value of 3. I know it's b because it's inside the square root and it's a multiplier on x. If you don't have parentheses, in other words, b is not factored out, then factor it out and then go on. Otherwise, you might say on an example like this that this function has been shifted to the right 6, but you would be totally wrong. It's only been shifted to the right 2. How do you know that? You know that because you factored the b value out. Pause now and take good notes of this. Now we're going to take a look at the cube root parent function. Now, last semester we studied the cubic parent function. This is the inverse of that. It's the opposite of that. If I want to undo a cubic, I apply a cube root. So here we are. This is the cube root parent function. This is what the parent function graph looks like. Here's what the table looks like. The domain and range are both all real numbers. Please know that. The x and y intercepts are both the origin, 0, 0. The key points again are the origin, 0, 0, and 1, 1. And I would also add -1 and -1. Now, this one has no restrictions because you can take the cube root of a negative number. Now, why is that true? Well, because take -2, for example. If you cube -2, you get -8. So that means the opposite, cube root of -8, is -2. So there are no restrictions on the domain of the cube root function. Now let's take a look at transformations of the cube root function. Again, with a, if it's greater than 0, it's a vertical stretch. If it's between 0 and 1, it's a vertical compression. And if it's less than 1, in other words, or less than 0, in other words, if it's negative, it is a vertical reflection. Now, if we do a horizontal stretch or compression or reflection, then the rules are exactly the same as they were for the square root parent function. If b is greater than 1, it's a horizontal compression by 1 over b. In other words, if I had the cube root of 4x, that would be a horizontal compression by a factor of 1 over 4. If b is between 0 and 1, then it is a horizontal stretch by a factor of 1 over b. So you see, I'm taking the reciprocal of b to describe my factor. So if I had the cube root of 1 over 5x, that would be a horizontal stretch by a factor of 5 over 1, or 5. And if b is negative, then I have a horizontal reflection. Now D shifts it up and down as always. Pause here if you need to take some notes on that. C shifts it left and right as always. Again, if you have a B value, you want to factor it out before you evaluate. Shifts left and right. And let me go back here. Yeah, make sure you factor out B. I also want to spend just a few minutes and talk to you about other radical functions and what they might look like. So these small numbers here in the radicals are called the roots. So we have a fourth root, a fifth root, a sixth root, a seventh root. Now check these graphs out. Check them all out. And what do you think even roots have in common? What do you think odd roots have in common? And how does this affect the domain and range? Think about that for a moment. Well, I think you can see that with even root functions, the domain and range is always going to be 0 to positive infinity. The x and y intercept is always going to be 0, 0. And that they are increasing from 0 to positive infinity. Whereas odd roots like 5, 9, 11, all have a domain and range of negative infinity to positive infinity. They all have an x and y intercept to 0, and they are all increasing from negative infinity to positive infinity. Also, let's talk about symmetry. Like even root functions have no symmetry. They're not mirrors of anything. But odd root functions are symmetrical around the origin. Now, it's time to do a couple of tricky transformations. If you took good notes, these aren't tricky at all, but let's try the first one. So we have this function, g of x is equal to 1/3 times the square root of negative x minus 4 plus 1. Now working left to right, we're going to note every single change from the parent function. So the first change we see is 1/3 outside of the square root parent function. So that tells us it's a vertical compression by a factor of 1/3. I know it's vertical because it's outside of the square root. Now let's, working left to right, what's the next change? Well, I got that big red negative sign on the x. It's inside the square root function, so I know it's horizontal. It also means I have a b value of -1. So it's a horizontal reflection for sure, because if I'm using my notes, it tells me that if b is negative, I have a horizontal reflection. But there's a b value, and it has not been factored out. So I must factor it out before going on. And when I do, I end up with negative times x plus 4. -1 times x plus 4. Now I can go on and evaluate C and D. Okay, now I have x plus 4 because I factored out -1 from both the x and the 4. So that means this function has shifted to the left 4. And finally, there's D. That means it shifted up 1. So if you work from left to right and take into account every single little change, you should get all of the transformation questions correct. This one, you're going to write the function. So we're going to do a horizontal compression by 1/2. We're going to shift it to the right 4. We're going to shift it down 3 and vertically reflect it. So we start with the parent function, and we need to compress it horizontally by 1/2. Well, we know that the compression factor for horizontal compressions is 1 over b. So that means I need to have a 2 inside the square root function, because I got to flip this. This is the compression factor. It's always 1 over b. So if I want a compression factor of 1 over 2, then I have to have a 2 here. And I am going to leave it factored out in this example of the answer. I'm going to go right 4, so that's x minus 4, down 3, so that's minus 3, and vertically reflected, it's vertical, so that reflection needs to go outside the square root symbol. Or, if I didn't want to factor it out, I could keep my negative outside the square root symbol because it's vertically reflected, and my minus 3 outside the square root symbol because it's vertically shifted down. But I could distribute the 2, and I'd end up with 2x minus 8. If I graph those, I'm going to get the exact same graph. Now, this is the end of the slideshow. If you did not get good notes, go back, watch it again, pause as often as you need to, and take good notes, because you'll be able to use your notes on your retake. If you have any questions at all, email me, give me the slide number or take a snapshot of the slide, send it to me, ask your question, and I'll get back to you as soon as I can. Good luck.